Hey, Mark. Thank you. I guess good morning, good afternoon, and good evening. That covers all.
Yes, and good night.
Good night. Yeah. So I'm Sandeep Srinivasan. I'm the founder of a startup called Verify. We're based in Palo Alto, California, and a distributed team. We have some folks in New York, some in Bangalore, and what we're trying to do is solve verification, hardware and software verification, by using machine learning and some advanced techniques in machine learning, such as reinforcement learning and also language models such as BERT and GPT-3. So my background is I started out my career many years ago at AMD in the microprocessor division. And since then, I've founded 4 startups. 2 of them have been in EDA, in the space of low power algorithms. And then 1 has been in the space of a mobile app that uses machine learning. And then the latest startup is Verify. So I'm going to share my screen. So the topic of our paper today is called Optimizing Design Verification Using Machine Learning and Doing Better Than Randon. So the primary authors for this paper are Bill Hughes, me, which is Sandeep Srinivasan, Rohit, Suvarna, all 3 from Verify, and Maithilee Kulkarni, who's with Xilinx, and Maithilee was also a intern at Verify, and she's significantly contributed towards this paper and more while she was at UT Austin working with Jacob Abraham. So the agenda for today's talk is we'll sort of briefly touch over some of the design verification challenges as we see them. And we'll pick a code coverage example as a toy motivational example and demonstrate how we might do better than random. And then we'll talk about how we apply machine learning techniques for this code coverage example. And then apply the same machine learning techniques for design verification. And we'll talk about 2 real-life test cases. One is a MESI cache controller design from opencores.org. And the other one is a RISC-V 64-bit design, which used to be called Ariane. And recently they've changed the name to CDA6. I'll touch upon a little about the future direction and our vision of what we see of machine learning's part in design verification. And then we'll conclude with a few of our thoughts and findings. So verification complexity is growing rapidly, as you can all attest to. This is a slide from DARPA, which is by Andreas Olofsson, dated 2017. I think it's a visionary slide where essentially what he's showing is that the cost of verification is approaching or greater than 50% of the cost of the total design. So this is a pretty alarming slide. And specific to hardware verification, there's about 4 verification engineers per design engineer. And the verification costs about 55% of the entire design cost and are rising. In addition, hard bugs are found late in the project. So now if you look at the software side, there's about 1.5 verification engineers per developer. And security bugs are typically found in production. So this is a growing challenge in the software industry as well. So there has been significant innovation in verification, UVM methodology, formal verification, so on and so forth over the last 2 decades. And if we could broadly categorize them as to how people use it currently is we use a lot of random tests. The efficacy of random tests are very low. but also the human effort in creating these random tests is low. Then we have constrained random, directed random, feedback random, and the effectiveness of finding bugs is sort of medium with this approach, and this is sort of a majority approach. And the human effort, I would say, is medium to high for these techniques. Now, obviously, directed tests give you the highest efficacy and effectiveness in finding a bug, but also it's the highest human effort. So the question we asked ourselves is, can we do better than random in humans in less time? So the answer is yes, but a new approach is required. So in order to explore this new approach of doing better than random and better than constrained random, we came up with this motivational example. And it's a toy example with 3 levels in a nested if condition. And the control flows to a lower level depth only if the values of ijk satisfy a particular range constraint. So for instance, I needs to be in the range of 1 to 26, and if j is in the range of 26 to 51, and if k is in the range of 51 to 76, we reach this line of code which is depth of 3. Now, depth equal to 3 is just a proxy for a very hard to reach condition or state, right? So this could be in hardware, could be in software, could be in a state machine. So the question we asked ourselves is, can we train a neural network to learn to produce the best ijk values without exhaustive random combinations? And then the other question we asked ourselves was, how does random selection of ijk perform as compared to a neural network that we will build? So now, just to put this in context, is the total number of states in this toy example is just 6561. The total number of atoms in the universe is 2 to the 287, approximately. The total number of states in a Go game, which Google famously beat Lee Sedol, the Go champion of the world, with an AI machine called AlphaGo, is 2 to the 602. And the total number of states in even a small microprocessor can be 2 to the 2 million. So the complexity and the state we're dealing with for hardware verification is significantly large. So now I'm going to just dive into what we applied specifically for this code coverage problem. We used a reinforcement learning algorithm called Q-learning. And Q-learning, essentially, the picture on the left shows a software agent that takes an action on an environment, and then the environment returns back 2 things. It returns back a reward, which is a scalar, and returns back a state. And based on this state and reward, the agent takes the next action. So it's a very simple formulation. And in Q-learning, the goal is to maximize what's called cumulative future reward, which is given by this equation called the Bellman's equation. So in this particular case, Q of pi denotes a particular policy or a set of distributions of reward and state and action that the reinforcement learning agent learns. And the formulation for the Bellman's equation is recursive in nature, where the state and action depends on the cumulative future reward, and our goal is to maximize the cumulative future reward. Now, the Q value is also called expected return, or the value of estimated cumulative future reward. You'll notice there's this factor gamma here, which is known as a discount factor. And the discount factor essentially discounts some of the future estimated reward because we can never actually truly predict what a future reward might be. Right? So for more on this topic, the book by Richard Sutton and Bartow is fantastic, and I'd encourage all of you to look at that if you haven't already. So the core of a DQN are Q values, as I just mentioned, where Q represents the discounted future rewards for a particular action for a particular state. So now DQN is just a Q learning algorithm that uses a deep neural network. And the reason we use a deep neural network is when the state becomes very large for a simple lookup table. So we use a DQN, which is a Q learning algorithm with a deep neural network. So now we applied the DQN to the code coverage example that I just showed you. And the RL agent, without any prior knowledge, learns by trial and error that I should be in the range of 1 to 25, J should be in the range of 25 to 50, and K should be in the range of 50 to 75 in order to maximize the average code depth reached. So you can see the results here on the right, where the blue line indicates random choices for IJK values, and the y-axis represents the average code depth reached, right? And the red line shows the verify RL agent that very quickly learns, after 500 episodes, how to produce an average code depth of 1.8 and above. And after 2,000 episodes, it quickly learns how to consistently produce IJK values that lead to an average code depth of 2.5 and above. So there's another factor in reinforcement learning where you can trade off exploration versus exploitation. And this is denoted in this graph by epsilon. So if you set epsilon to 0, that means you're always exploiting. So in this particular graph, maybe it would have sort of plateaued out at 1.8. Now, when you set epsilon value slightly higher than 0, it goes into this mode of exploration where it periodically explores with random IJK values. And that's where you see a jump in the learning. So now we apply the same DQN for design verification. And the setup for DV, for design verification, is depicted by this diagram on the left, where you have a design under test, and then you've got an initial random knob settings for the device under test that then goes into a simulator, and the simulator output then goes back into the reinforcement learning agent, which produces the next set of knobs to feed back into the simulator. So you can think of it just like the knobs for the simulator are DV controls, design configuration, plus ARGs, and just like I explained, it's as simple as choosing the IJK values. And we also pick an output output metric to optimize. In the code coverage example, our goal was to optimize average code depth reached. But with design verification, our goal can be optimizing coverage, code coverage, function coverage, optimizing specific things like FIFO depths, victim buffer counts, that all depend on the knob settings. So the knobs need to be controllable and observable to make a difference to the output. So the DQN is modeled, or this problem is modeled as a MDP, Markov decision process, where it's a mathematical model for control systems where the current state is sufficient for the software agent to take an action. we used a deep Q network here, a DQN, to train an RL agent to learn a policy of Q values. And in addition, if you had prior simulation outputs that we had in this particular case, we use that as prior ground truth for what's called an experience buffer that the reinforcement learning agent can learn from. So the first test case, as I mentioned, was a MESI cache controller design. So the cache controller design supports a quad-core CPU, and it's a 4-way set associative cache of size 256 KB, one for each CPU. It has a 4-bit offset, 12-bit index, and a 16-bit tag. And this design is available at opencores.org, and I'll also share, we've put this design up on our website for you to try this experiment live. So the knobs, which is the inputs to this test bench to generate constrained random sequences, are the following. There were 16 knobs for distribution of commands, 4 for each CPU, and the commands look like, broadcast read, broadcast write, read write, no op, and there's 12 knobs for controlling the address, 3 for each CPU. And like I mentioned, offset, index, and tag. So there's a total of 28 knobs that we wanted to find settings for. Now the output we captured from the test bench was a FIFO depth for each CPU at each cycle. And what we're measuring as a reward function is the average FIFO depth of all 4 CPUs. And our goal is to increase the average FIFO depth across all 4 CPUs. So the RL algorithm we used for test case 1 was again exactly like the DQN we modeled earlier. And the simulation setup looks like this, where we have the device under test running simulations. In this particular case, we used Verilator. And then from the results of the simulator, we essentially parse the rewards. In this case, the reward was the average FIFO depth. And that's fed into the RL agent. And the RL agent now produces the next knob settings of those 28 knobs that I just described for the next simulation, and so on. So the initial data set consisted of a set of random knobs and their average FIFO depths. And like I mentioned, this data set is fed into a DNN or an RL agent that learns a function that maps the knob settings to the FIFO depth. So in effect, it learns from the reward function, which is the average FIFO depth, to produce the next set of knobs. So the DNN, once trained, can be used to generate new knob settings and predict the average FIFO depth values. And again, once trained, the DNN essentially simulates the output for any new unseen knob settings, right? So this is the power of a deep neural network, where it can actually fit a function to even highly nonlinear behaviors. So the results of test case 1, which is maximizing the average FIFO depth, were really interesting. So the blue line again, in this case, was just random choices of those 28 knobs. And the x-axis indicates the number of episodes. Each episode is one time step. You can think of it as one time step or one simulation. And the y-axis is the average FIFO depth. The FIFO depth goes from 0 to 15. So as you can see, the orange line is the reinforcement learning agent. And within 400 episodes, it starts producing average FIFO depths of 9 and above, which is a significant learning in 400 episodes. and then sort of continues to plateau out a little bit. So now you could say that, yeah, you could probably get high FIFO depths even with random and constrained random, but then you're leaving that to chance. What we were really trying to show here is, can a reinforcement learning agent learn enough to do better than random in a shorter amount of time? So this is the same data for the test case 1 results shown as histograms. So if we look at the first baseline simulation with random inputs, so this is no machine learning, just sort of random UVM generated knob settings. What this is showing you is the distribution of average FIFO depths, and the y-axis is showing you the occurrence. So you can see the distribution is average FIFO depths between 1 and 5, very few 5s. And after one iteration of reinforcement learning, the distribution shifts significantly to the right, producing very high average FIFO depths. And after 2 iterations, you can see the distribution shifting even further to the right, which is what you want. So a lot of high FIFO depths, so almost 50, 45 occurrences with FIFO depths of about 10. So this is typically what we see with our reinforcement learning agent as applied to a hardware verification problem to optimize coverage, FIFO depth, and other signals that are hard to reach. So to run this cache controller, you can log into our website. It's free, and you'll be able to run this experiment live. So the test case number 2 was a RISC-V Ariane design, which has been renamed to CV-A6. So it's a 64-bit processor, and it looks like this. It has a 6-stage pipeline, in-order issue, out-of-order write-back, and we focus primarily on the data cache. And in the data cache, what we focused on is what's called the victim buffer. So the data cache is here in blue. So the data cache stores recently accessed data from memory. For all of you processor guys, you might know this already. And new cache allocations cause existing lines in the data cache to be evicted, right? Now, these modified evicted lines are held in what's called the victim buffer. So this is a very hard to hit condition where many things have to happen. There has to be collisions in address. There has to be collisions in the data cache for this to occur. So that's why we chose as our target to optimize the victim buffer count. So just a little about the design complexity of victim buffer. A cache line eviction and memory writebacks is complex, as I just mentioned. Victim buffer full requires back pressure for cache refills. That means there's got to be a lot of instructions backed up for victim buffers to get full. And why do you want to fill up a victim buffer? Because it uncovers other parts of the design that have not been exercised yet, perhaps. So the output we captured from this test bench is the average number of victims and the percentage of hitting max victim buffer count. And our goal was to increase the victim buffer count. So again, the simulation is set up exactly like the previous one, which is the FIFO test case, with the exception that in the FIFO test case, we had the 28 knobs that were set up directly with the test bench. In this particular case, what we were doing was we were using the Google instruction generator, and we were generating, or our RL agent is generating knob settings for the Google instruction generator. And the initial knob settings for the Google instruction generator are random. So the RL agent learns from each iteration as to which knobs impact the victim buffer occupancy. And then the RL agent subsequently produces knob settings for the next simulation run and feeds that into the Google instruction generator. And eventually it learns how to generate the settings which increases the victim buffer count, which is our reward function. So the list of knobs in this particular case were, there was a wait for the load store jump branch instructions. There's a wait for other instructions. There's a wait for load, wait for stores, wait for jumps, wait for branches. And there's a tag and an index string. So these are the knob settings that our RL agent was generating for the Google instruction generator. So the results again were pretty dramatic. The average victim buffer occupancy increased from 0.9 to about 1.6 in just 3 iterations. And again, a very similar picture. The blue line shows you random inputs to the Google instruction generator. And it shows you that the average victim buffer count never exceeds 0.9. And with the reinforcement learning agent that's generating knobs, very quickly, within 4 iterations, it starts to learn how to generate knob settings such that you get an average victim buffer count of 1.6 and above. So the maximum victim buffer count is 4. So essentially what the RL agent has done is identified the salient knobs and salient knob settings to the input to the Google instruction generator and exploits them while exploring as well, as I mentioned earlier. So these are some of the results. Again, from case 2, this is iteration-wise average number of victims, and the x-axis is iteration, and average number of victim buffer count is on the y-axis, and you can see the RL agent starts producing much higher average number of victims than a random choice of inputs for the Google instruction generator. We also plotted the histogram of the average number of victims versus the occurrence. So the mean of the average number of victims is 0.95, and it increased pretty dramatically to 1.55 just in 4 iterations. The other metric, as we mentioned earlier, was we were also interested in recording the percentage of hitting max, which is how many times did you hit max victim buffer count, right? And the mean of that also significantly increased in 4 iterations, as shown in these 2 plots. So I want to talk a little about the future direction for ML for DV. We think reinforcement learning algorithms to handle large action spaces are required. This is an active area of research, and some very promising algorithms are what's called DDPG, Deep Deterministic Policy Gradient, and Soft Actor Critic, which is actually DDPG is based on Soft Actor Critic, but there's a particular algorithm called A3C where it can handle large action spaces. And we're also exploring statistical algorithms such as contextual bandit and bandit algorithms. And in addition, in simulation RL or online RL. So what we showed you currently was sort of batched RL, where we take a bunch of simulations, learn from it, and produce a bunch of knobs for the next simulations. Online RL would be sim by sim, the RL agent learns. So we also feel RL will be deployed very widely to shorten debug and development time, automate bug finding, and reduce compute cycles used for verification. So in conclusion, we've demonstrated the value of using machine learning techniques in industrial design, such as the FIFO controller and the RISC-V 64-bit. And we've also demonstrated that it does significantly better than constrained random methods. Now, DNN provides a mechanism to fit any nonlinear function that can mimic extremely complex behaviors, perhaps even of a simulator. So using RL for DV, we believe can save months of verification resources for coverage improvement, early bug finding, and in addition, very importantly, can also dramatically reduce the energy used to verify a chip. So with that, I thank you for your time, and I'll open it up to any questions that you may have.
Thank you very much indeed, Sandeep. It was very, very interesting indeed. There are some questions, so let's go straight in. Can you see them? First one's
yeah. Okay, Chris Edwards, are there risks in selecting metrics for RL machine learning models? The highly targeted ones, like FIFO buffer depth, may make sense. They explore a particular verification hypothesis. But more general targets, such as coverage, seem to present a danger of focusing on easy coverage that may leave difficult to reach states unexplored compared to more targeted goal rewards through coverage numbers wind up looking good. Is that fair? Wow, fantastic question. So I'll try to answer it as well as I can in the given amount of time. So, like I mentioned earlier, there's a stage for exploration and exploitation. And if we're looking at just coverage, you mentioned easy coverage. But one of the things that you can also learn from coverage is the incremental coverage added by a particular test or a particular regression, right? So rather than using overall coverage as a metric, you could also choose to use incremental coverage as a metric, which can be more representative of doing exploration on the design. I hope that answers it. I'm happy to chat more. So this is from Sumedha Bengali. I'm sorry if I mispronounced the name. In both test cases, the RL learning output also plateaued after the first bump. Was it because it was already close to 100% of the reachability, or were they hard to hit waivable conditions? Yeah, a great question. So it does plateau, and as we simulate further, it does hit close to 100%. And we didn't waive any conditions on both these test cases. There were none to waive. Benedict Shimanek, do you compare results from ML also against constrained random testing done by VE traditional way? Yes, we did. And we're dramatically, significantly better. Or the RL agent is, rather.
Thank you very much for answering those questions. Are there any more from anybody? We're coming hard up against the end of the time slot. I will post a link in the chat. I would very much appreciate it if the three presenters could join in with the virtual environment. I suggest we congregate in the blue area, which is to the left as you enter. Well, you go up the stairs and then it's the room on the left-hand side of the main hall. I would really appreciate if everybody came in there, particularly if you have questions for the presenters. And it would be great to see that platform and to use that as a way of discussing what we've just heard. Just before we go, one last question from Christian Slav. If you would like to answer that, and then I would ask you all to come into the meeting, into the virtual room.
Okay, this is a good question from Christian. Christian says, how scalable is a technique for large number of coverage elements, not only for a large number of nodes? In the real project, there are hundreds and thousands of coverage points to be hit. Can these be targeted all at once? So that's a great question. The answer is yes. And the answer is the following, which is you can either come up with a function that encapsulates all these coverage points by ANDing and ORing them together, if you will, in the most simplistic manner, or look at it as a distribution that can all be hit. Happy to chat about that more in detail.
Yeah, absolutely. Well, let's if everybody follows that link now and gets into the virtual room, let's continue those discussions because they were really, really good. Thank you very much indeed, Sandeep, and thank you to all three presenters. We're